Hi and welcome back to another LeetCode video. Today we're going to start to explore the advanced graph section, and I have not completed these problems yet. Maybe I have completed some of them a year or two ago, but I haven't done it recently, and I'm currently going through the entire list. And the first problem that we are going to take a look at is the network delay time problem. It's a LeetCode medium graph problem, and we're given a network of n nodes labeled from 1 to n. And we're also given times, which is a list of travel times between the nodes. So we are actually dealing with a weighted directed graph here. And each entry in our times array is the source node u, the target node v, and the weight I, where wi is the time it takes for a signal to travel from the source node to the target node. And furthermore, we're giving a node k from which we will send a message, and we should return the minimum time it takes for all of the nodes to receive the signal or the message. If it is impossible for all n nodes to receive the signal, we should return -1. Now here's a nice example. Let's just take this to the drawing board. And so this is what we're dealing with. You can see here we have the node 2 as an edge to the node 1, a directed edge with weight 1. This is the weight here. The last bit is always the weight. And you can see the next edge is from node 2 to node 3, also with weight 1. And then we have an edge from node 3 to node 4 with also the edge 1. Now we're starting at k, at node k, which is 2. So we're actually starting here. And as you can see, we can reach all of the nodes. And how much time it takes? Well, we have to sum up all the edges on the longest path to all of the nodes, right? So here we have just 1, and this edge would be 2, so the maximum 2, and that's what we're going to return. Now the next graph is just a graph where we have, well, we know that we have 2 nodes. We have the node 1, we have the node 2, we have an edge between them, and the weight is 2. We're starting at node 1, so the total time it takes is, of course, wait, let me see. The edge weight is 1, so it's not 2, it's actually 1. So that's why the output is also 1. Now finally, we have another example where we also have a graph that has node 1 and 2 and an edge between them of weight 1. But this time we're starting at node 2, and from node 2 we can't go anywhere, so we will need infinite time to reach node 1. And the way we're going to approach this problem is we're first going to transform this set of edges into a graph structure, such that we have, the typical graph structure that we use for LeetCode style problems, where we say that a graph of with a key of one of the vertices, for example 2, that would contain a set of all the connected neighboring nodes. So that would be U1, I guess, U2, etc., depending on how many there are. Now what we also need is we're going to need a weight, I guess, hash set, where we say, well, the weight of an edge from U to V is equal to a numerical value, whatever that value might be. And we will need this to look up, what are the costs to go from one node to the other. Of course, in the context of the problem, the cost refers to the time that it takes to travel to those nodes. Now, what we also need to maintain is we need to maintain a value that tells us when we were able to reach a node after how many units of time. So that then when we have to return the maximum time it took to reach all of the nodes, we can just take the maximum of all of those values. And for that, we're just going to use maybe an arrival hash set, and for every single node, it will contain however many units of time it took to reach that node. Right. So with that, let's go back into the code. And the first thing we're going to do is actually we're going to build the graph. Build graph. I like to put this into a little helper function, just to have it in its own little, how do you say, capsuled piece of code logic. That's what I like to do. So we will use a default dictionary here, and that will contain a set. And then we will also initialize the cost hash set that will contain the delay that it takes to reach one node from the other node. So now we're going to iterate over our times array, and we are just going to use the u, v, and w. So u, v, and I guess the weight in times, and we're going to add an edge from node u to node v, and we're also going to remember the weight of that edge. And well, we have to put it as a tuple, because a tuple is hashable, and since the graph is directed, we only have to add it in one direction. We don't have to add the reverse edge as well. So that is going to be equal to the weight. And finally, we'll just return this. Return the graph and the cost hash set. And outside of this function, we're just going to call that function build graph. Right. Now, I said we also need an arrival hash map. And yeah, I'm just going to set this. Now, there's a reason why we're giving the value n for the number of nodes. And the reason is that there might not be an edge between all of the nodes. So if we go through the list of the edges, you and we might never assume all the values that are between 1 and n, right? So if we want to determine whether we can reach all of the nodes, we need to check, if all nodes were reachable, not just the ones that had edges to them. And obviously, if the graph is not connected, there's no chance that we'll ever reach all of the nodes, so regardless of on which node we start. And so we will initialize our arrival time array with, with the time for how long it takes to reach them. And by default, we're just going to set it to float infinity. And if you know Dijkstra, there's some similarity to the Dijkstra algorithm here, where we initialize the cost to reach a node with infinity, because we haven't reached that node yet. But as we do our search through the graph, we will update these arrival times, of course. For v in range 1 to n plus 1, because the end of the range in Python is exclusive. Right, so, well, now all we need is a traditional graph traversal. And so we're going to need some kind of a queue. I like to use a deck for that. So I'm going to use a breadth first search algorithm here. You can also put in a recursive algorithm. It really does not matter at all. Really doesn't matter. But the deck, I find that easier to do. Now, we know that we're going to start at node k, right? So that's going to be our seed for our queue. And since we are at that node, well, we should also update the arrival time for k to be equal to 0, because we start there, we're already there, we don't need to get there. Right, so now we just continue to explore the graph. So while we have an element in the queue, we're going to pop that element out left, and I'm going to use the source node, because next we're going to iterate over all of the neighbors of the source node, and we're going to use our graph hash map for that. As you remember, we have all the neighbors of a node are stored in the hash map at key of the source node, and that is a set, and now we're iterating over all of the elements of that set. Now, first, we're going to need to get a handle of the edge again, so that we can, do lookups of the cost in our cost array. I'm just going to define here as a tuple from source to destination. And we know it exists, otherwise we wouldn't have pulled out destination out of the graph. Right. So now, what is now? Well, we now need to compute what is the time it takes from source node to reach the destination node. So time to dst equals, of course, it's the time And I said before that we refer to this as, the arrival time of our source node plus the time it takes to travel along the edge. So we'll have arrival of the source node, that's the arrival time there, plus the cost to travel along the edge. And now, well, it could be that, it's more expensive to reach that node. Say if we had, I don't know, if we had here in this example, if we had another edge here that has maybe weight 2, then it would take 3 units of time to reach the node 4 from 2 if we go over the node 1. But it would only reach 2 units of time to reach 4 if we go over the node 3. So we only want to update the arrival time of a node when we found a shorter way in terms of the time that it took to reach that node. Otherwise, we're not going to bother. And basically, our exploration stops at that point. So we have to have a check if time to destination is more than the current arrival time to reach the destination. Well, that means we should actually go to the destination. And we should update the time that it takes it, and we're going to append that to our queue. So the destination again. Because now that we found a shorter way to reach the destination, we might find, the neighbors of the destinations might be reachable in shorter amount of time as well. So we need to continue to explore from the destination node in this particular case. Right. So at some point, because we're not going to find a shorter time to the destination, this while loop will terminate. We won't have any elements anymore in the queue. Now it's time to check whether we still have any elements in arrival that we did not update, that we did not reach. And that's easy to do. So if we can reach all of the nodes, the result is just going to be arrival, or the maximum arrival time in our arrivals hash set. A hash map. Now, if the result, however, is equal to float infinity, that means one of the arrival times of one of the nodes has not been updated. The node has not been reached, and in this case, we have to return -1. Result equals -1, and then we just return result. That's everything there is to it. So you really just need to keep track of, well, you need to pay attention where you're going to go. And the condition to terminate the traversal at a specific node is that if you can't reach another neighbor in a shorter amount of time, that you could already reach that neighbor. Now, in terms of time and space complexity analysis, let's have a look at that. So, well, how much do we need to build the graph? Well, obviously, we need to iterate over all of the edges, right? So, number of edges, time, and we're also storing every edge, so definitely need that amount of space. But we also need definitely O of n space. N is the number of nodes because we are initializing our arrival array. So O of n, and n is the number of vertices, right? So we actually have also O of e plus v time because it takes number of vertices time to do this. And now the exploration, well, you have to think about how many times are you going to update values in the graph. So let's say you have a couple of nodes. Maybe we should draw them as dots or something. And let's say you can reach a node like so, maybe at a high cost, but you can also reach them maybe at a lower cost. This might be 1, 1, 1. And from here, maybe you have something here as well. 1, 1, 4, 2. So if you start at this node, it's kind of random which edge you take first, right? So it could be that you take this edge first, this long one, then you have your value of 10, then you start to explore the rest of the graph. And then later you discover this shorter edge, right? And so this can actually result in, well, I'm not quite sure actually how much precisely, but maybe we can come up with an even better example for the worst case. So in the worst case, we're going along the longest edge first and then the cheaper edges, right? So let's say we have a very long, expensive edge here. And then we have here one that is slightly less expensive and even less expensive. Oh, made this maybe 98, 96, and so on up until maybe cost 1. And we also have edges that go here, but that only cost 1. So that means if we're unlucky, what will happen is we will travel along the longest edge. We will explore all the nodes here, which are half of the nodes. Then we pick this edge and we start exploring again half of the nodes, and so on and so on. So this would be actually O of n squared, right? Because at every step we take n steps through all the nodes, and then we have to do it again and again and again. So this is, I think that is correct, that we will have the time that it takes in the worst case is going to be number of edges and number of vertices squared. Now we can reduce this if we change the logic by which we pick the next edge. So if we changed our deck, well, not the deck, but if we actually use a Dijkstra's algorithm to always start to pick the next edge that has the lowest weight, I think we could bring it down to something logarithmic. That's something. I have to review how Dijkstra actually works. And I have not prepared that for this video. But let's just see if this this approach works. Passes the test cases. Okay, and it passes the submission as well. So yeah. So for optimization, we would definitely want to pick, well, we probably want to use Dijkstra, where we pick the next edge from Dijkstra works like this, if I remember correctly. You have a bunch of nodes, and you have edges between them, and they all have kind of weights. And what you do is you keep a list of all of the nodes that you've already explored, circled in blue here. And now the next edge that you visit is the one that has the smallest value, because you're trying to minimize the costs or the delay for the signal to reach anywhere. So here you would pick this edge. Now this blue node becomes part of your set of nodes that you will consider to continue to explore from, right? 1, 9, 6, and then now we evaluate again. Okay, which node has the edge with the lowest weight? Well, it's this edge is the next one. So now in the next step, we consider, okay, which edge from any of the blue nodes has the lowest weight? And obviously it's this edge, the 3 edge. So this node now becomes part of the set. And then we pick this edge because it's the one with the lowest value. Now we go to 4 because 4 is the next lowest value. And so forth and so forth. And then we check, if we take another, well, actually now we have 4. Now we have to take 5, the 5 edge, to this node. And we have to check if 3 plus 5 is smaller than just 1. Of course it isn't, so we stop here. But yeah, and then we have to take the edge here, the 6th edge, and obviously 4 plus 6 is 10 is larger than 1 plus 2. So we don't go any further here. Now we have 2 9s to pick from. I believe that's random now, which one we pick. We can pick either one, and then maybe this edge was this way. And then finally the other. Well, actually, I think I'm not quite sure if in Dijkstra we can stop as soon as we've seen all nodes, or if we actually need to complete all of the edges. But yeah, that's something to research. I believe the Dijkstra's algorithm would be the optimum here, but this approach also works. And yeah, therefore I will check off this problem from the list.